Hello everyone and welcome back to our channel. Today we are going to discuss about the thermal reserve zone in blast furnace operation. So let's start. Thermal reserve zone, TRZ. The TRZ is a region in the blast furnace where the temperature of solids and gases are nearly identical, typically between 800 degrees Celsius to 1000 degrees Celsius. This zone is characterized by minimal heat exchange between the solids and gases. 1. Temperature uniformity. The temperature of solids and gases are nearly identical, indicating a state of thermal equilibrium. 2. Minimal heat exchange. The heat exchange between solids and gases are minimal, which helps to maintain a stable temperature. 3. Indirect reduction. The TRZ is also known as the indirect reduction zone, as most of the indirect reduction of wustite, FeO, occurs in this region. Importance. 1. Wustite reduction. The TRZ provides an opportunity for wustite to be reduced indirectly, which is a crucial step in the production of iron. 2. Furnace efficiency. The extent of the TRZ is important, as it can occupy a significant portion of the furnace volume, up to 50 to 60% in a well-run furnace. 3. Iron quality. The TRZ plays a critical role in determining the quality of the iron produced, as it allows for optimal reduction of iron oxides. Benefits. 1. Improved efficiency. A well-developed TRZ can improve the overall efficiency of the blast furnace. 2. Increased productivity. By optimizing the TRZ, blast furnace operators can increase productivity and reduce energy consumption. 3. Better iron quality. A stable and extensive TRZ can lead to the production of high-quality iron with minimal impurities. Operational considerations. 1. Temperature control. Maintaining a stable temperature in the TRZ is crucial to ensure optimal indirect reduction and iron production. 2. Gas flow. Controlling gas flow rates and distribution can help to maintain a stable TRZ and optimize indirect reduction. 3. Coke quality. The quality of coke used in the blast furnace can impact the stability and efficiency of the TRZ. Blast volume and temperature profile. The blast volume, which is the volume of air blown into the blast furnace, plays a crucial role in determining the temperature profile. Increasing the blast volume can lead to higher productivity, but it also affects the temperature profile. Effects of increased blast volume. 1. Increased heat exchange zones. When the blast volume is increased, both the upper and lower heat exchange zones expand. This is because the increased gas flow rate enhances convective heat transfer, leading to a more rapid exchange of heat between the gases and solids. 2. Decrease in thermal reserve zone. As the blast volume increases, the thermal reserve zone, TRZ, decreases. This is because the increased gas flow rate reduces the residence time of the gases in the furnace, making it more difficult to maintain a stable temperature profile. 3. Quantitative impact. A 20 to 30% increase in blast volume can lead to a 10 to 15% decrease in the TRZ. This reduction in TRZ can have significant implications for furnace operation and efficiency. Top gas temperature. 1. No increase in top gas temperature. Interestingly, the top gas temperature does not increase until the TRZ is depleted. This is because the TRZ acts as a buffer, absorbing excess heat and maintaining a stable temperature profile. 2. Importance of TRZ. The existence of the TRZ is critical in maintaining a stable temperature profile and preventing excessive heat loss through the top gas. 3. Implications. Productivity versus efficiency. While increasing blast volume can lead to higher productivity, it can also compromise furnace efficiency by reducing the TRZ. Optimization. Blast furnace operators need to optimize blast volume and other operating parameters to balance productivity and efficiency. Monitoring and control. Continuous monitoring of the temperature profile and TRZ is essential to ensure optimal furnace operation and make adjustments as needed. Blast temperature and temperature profile. The blast temperature, which is the temperature of the hot air blown into the blast furnace, plays a significant role in determining the temperature profile. Increasing the blast temperature can have several effects on the furnace operation. Effects of increased blast temperature. 1. Reduced Teuer carbon rate. When the blast temperature is increased, the Teuer carbon rate, the amount of carbon consumed at the Teuers, decreases. This is because the higher temperature of the blast air reduces the amount of carbon required to achieve the same level of heat input. 2. Reduced gas volume. With a lower Teuer carbon rate, the volume of gases produced in the furnace decreases. This reduction in gas volume means that less heat is carried to the upper part of the furnace. 3. Steeper temperature gradient. As a result of the reduced gas volume, a steeper temperature gradient develops in the lower part of the furnace. This means that the temperature difference between the lower and upper parts of the furnace increases. Impact on heat exchange zones. 1. Reduced lower heat exchange zone. The increased blast temperature reduces the lower heat exchange zone. This is because the higher temperature of the blast air reduces the need for heat exchange in the lower part of the furnace. 2. Increased thermal reserve zone. Conversely, the higher blast temperature increases the thermal reserve zone, TRZ. This is because the reduced gas volume and steeper temperature gradient lead to a more stable temperature profile, allowing for a larger TRZ. Benefits. 1. Improved efficiency. Increasing the blast temperature can improve furnace efficiency by reducing the amount of carbon consumed and minimizing heat losses. 2. Increased productivity. A larger TRZ can lead to more stable and efficient furnace operation, potentially increasing productivity. Operational considerations. 1. Optimization. Blast furnace operators need to optimize blast temperature and other operating parameters to achieve a balance between efficiency, productivity, and stability. 2. Monitoring and control. Continuous monitoring of the temperature profile and TRZ is essential to ensure optimal furnace operation and make adjustments as needed. Oxygen enrichment of blast. When the blast air is enriched with oxygen, the percentage of nitrogen, N2, decreases, and the percentage of oxygen, O2, increases. This change in blast composition has several effects on the furnace operation. Effects of oxygen enrichment. 1. Reduced volume of air. With oxygen enrichment, the volume of air required to burn 1 kilogram of carbon, C, decreases. This is because oxygen is a more reactive gas than nitrogen, and less air is needed to achieve the same level of combustion. 2. Reduced volume of gas produced. The volume of gas produced per kg of C burnt also decreases with oxygen enrichment. This is because the reaction produces less gas, mainly CO and CO2, when oxygen is used instead of air. 3. Reduced sensible heat input. As a result of the reduced volume of air and gas, the sensible heat input through the air decreases. This means that less heat is carried into the furnace through the blast air. 4. Reduced thermal capacity of Teuer gas. The thermal capacity of the Teuer gas, the gas mixture at the Teuer, also decreases with oxygen enrichment. This is because the Teuer gas has a lower volume and heat capacity. Impact on temperature profile. 1. Increased raft. The reduced activation flame temperature, raft, increases with oxygen enrichment. This is because the reduced sensible heat input and thermal capacity of the pure gas lead to a higher flame temperature. 2. Reduced thermal reserve zone. Oxygen enrichment leads to a reduction in the thermal reserve zone, TRZ. This is because the pure gas carries less heat to the upper part of the furnace, resulting in a smaller TRZ. 3. Increased upper heat exchange zone. The upper heat exchange zone increases with oxygen enrichment. This is because the reduced TRZ and increased temperature gradient in the upper part of the furnace lead to more intense heat exchange. Implications. 1. Furnace operation. Oxygen enrichment can lead to changes in furnace operation, including changes in temperature profile, gas composition, and heat transfer. 2. Optimization. Blast furnace operators need to optimize oxygen enrichment levels and other operating parameters to achieve a balance between efficiency, productivity, and stability. 3. Monitoring and control. Continuous monitoring of the temperature profile and TRZ is essential to ensure optimal furnace operation and make adjustments as needed. Coolant injection. When a coolant, such as steam, oil, coal, gas is injected through the tuers, it has several effects on the furnace operation. Effects of coolant injection. 1. Reduced draft. The injection of coolant reduces the reduced activation flame temperature, draft. This is because the coolant absorbs heat from the furnace, reducing the temperature of the gases and solids. 2. Smoother temperature gradient. Coolant injection leads to a smoother temperature gradient in the furnace. This is because the coolant helps to distribute heat more evenly, reducing the temperature differences between different parts of the furnace. 3. Reduced thermal reserve zone. The thermal reserve zone, TRZ, decreases with coolant injection. This is because the reduced draft and smoother temperature gradient lead to a more uniform temperature profile, reducing the size of the TRZ. Impact on heat exchange zones. 1. Increased heat exchange zone. The heat exchange zone increases with coolant injection. This is because the gas with lower thermal potential needs a greater furnace volume to heat the products, resulting in more intense heat exchange. 2. Greater furnace volume utilization. The increased heat exchange zone means that a greater volume of the furnace is utilized for heat exchange, which can lead to more efficient furnace operation. Implications. 1. Furnace operation. Coolant injection can lead to changes in furnace operation, including changes in temperature profile, gas composition, and heat transfer. 2. Optimization. Blast furnace operators need to optimize coolant injection rates and other operating parameters to achieve a balance between efficiency, productivity, and stability. 3. Monitoring and control. Continuous monitoring of the temperature profile and TRZ is essential to ensure optimal furnace operation and make adjustments as needed. Stock line. The stock line refers to the level of the burden, raw materials, in the blast furnace. Changing the stock line can have significant effects on furnace operation. Effects of lowering stock line. 1. Decreased thermal reserve zone. Lowering the stock line decreases the thermal reserve zone, TRZ, which can hamper the indirect reduction of FeO. This is because the TRZ is critical for the efficient reduction of iron oxides. 2. Poor burden distribution. A lower stock line can lead to improper distribution of burden, resulting in poor bed permeability and non-uniformity of gas distribution. 3. Increased upper heat exchange zone. The poor bed permeability and non-uniform gas distribution can lead to increased heat exchange in the upper part of the furnace, which can negatively impact furnace efficiency. Impact on furnace operation. 1. Coke rate. A change in stock depth can affect the gaseous reduction of wustite and hence the coke rate. This is because the coke rate is influenced by the efficiency of the reduction reactions. 2. Metal quality. Maintaining a constant stock level is crucial for uniformity of furnace operation and metal quality. Changes in stock level can lead to variations in metal composition and quality. Furnace height. The height of the blast furnace can also impact furnace operation. Effects of increasing furnace height. 1. Increased thermal reserve zone. Increasing the furnace height can increase the thermal reserve zone, TRZ, without significantly affecting the top temperature. This is because the additional height provides more space for the burden to undergo reduction reactions. 2. Improved furnace operation. A larger TRZ can lead to more efficient furnace operation as it allows for more complete reduction of iron oxides. Implications. Optimization. Blast furnace operators need to optimize stock line and furnace height to achieve a balance between efficiency, productivity, and metal quality. Monitoring and control. Continuous monitoring of the stock line and furnace height is essential to ensure optimal furnace operation and make adjustments as needed.